Hello, I wanted to use these slides here to try to address the question that we had in class with respect to distributions. So whenever we're modeling things, we're modeling the distribution of y, and ultimately with HLM, the distribution of, or the associations between the y's. And so I wanted to give a little background first about what that looks like with regression, but then generalize it to mixed models. So we'll actually be using mixed models in this context. So first with regression, well, I thought, okay, so first with regression. In the context of regression, the way that I'm going to talk about this is with respect to complete vectors, so not single observations. So what that means is that our actual regression line, so whenever we model these things, we have a y vector, and I'll use the little tilde there. This vector is going to be of length n by 1. And so it's literally the observations of every single person. And we are trying to predict that entire vector or model that entire vector using regression. And so it's simultaneous, it's for every single observation. So that means to do this, we end up having the data matrix X. Now that data matrix, you could imagine it being similar to what the data set looks like in something like SPSS. The only added feature that we will add to it is they'll have a column of ones, and that's going to pick up that intercept. But then we have all of our different variables represented in here. And then that is going to be post-multiplied by vector beta. So X, if there's a row per person, there's going to be n rows, and there's going to be a column per variable plus the column of ones. And so that means that thing's going to be n by p plus 1. The p comes from Renscher. So if you had multivariate, we would use p to indicate the number of variables that we have. Or actually, Renscher may actually use q in that case because it's x. I'm just going to stick with p as the number of variables. Now because of that, that means that beta here is going to be a p plus 1, plus by 1 vector. And so this is literally your regression coefficients. So it's got the intercept 1 all the way up to a beta p. And then what happens is we add to it an error vector. So that thing, again, is just full of the errors that we would normally have per person. So in regression, even though we don't always have it this way, whenever we represent them as vectors, what happens is we're trying to predict an entire distribution or an entire vector of y. So it is y that we're trying to predict. And that means that we are actually making the claim that the vector y has a distribution. Now this is going to be an n-dimensional distribution. So it's multivariate normal. And we are going to say that that vector is centered at what we would predict. So it has a mean of x times beta. And remember, this is coming from this thing right here. And then it has this variance covariance matrix. Now remember, y is n-dimensional. So a variance covariance matrix is going to be an n by n variance covariance matrix. So we're really talking about the relationship between any y observation with any other y observation. And in the context of regression, we make the assumption of identically and independently distributed. So what that means is, first, identically. We assume that the error terms, or the variability around y, not explained by x and b, so kind of my error part, we assume that they are identically distributed. So the variability of those will always be the same. So what that means in terms of my variance covariance matrix is for every single person, there's a sigma squared. Now we also assume that they are independently distributed. So they're identically and independently distributed. That means the covariance between any two people is going to be equal to 0. So really there's zeros on the off diagonal. And the identically distributed assumption is talking about sigma squared. Now the way we could write that in this context of this distribution is we'll write a sigma squared times I. And that I is going to be the identity matrix, but it's n by n. And so that's how this part right here ends up being this thing. Now, most people don't even realize that lingering in the background is a huge variance covariance matrix that's n by n. And so that's lingering in the background, the assumption of regression. And the way we end up doing it is we say, well, if every single error is identically and independently distributed, and they're all centered at 0 with the same variance sigma squared, then we can just use those as a set of observations from that distribution to estimate what the variance is. So we usually gloss over, especially in an intro stat. Now in multivariate, we start to talk about this, but whether or not it makes sense is something that kind of you have to settle in for a while. So that's regression. This is the distributional assumption that's made in the context of regression, and that is the thing that we then fit. So if we can assume that y follows this distribution, we can actually solve for things like beta in such a way that y is as likely as possible, because now we know where it should be centered, and we can compute the likelihood of that vector. Okay, now that's regression. So we move on to mixed models. Now in the context of mixed models, things are going to look a little different. So first, we need to get to notation-wise, and I'm going to move you in a direction of where the books go to for mixed models. So that means things are going to look a little different for us. So for example, if we go to a simplified example, we're going to do a random intercepts slopes model. So that means in HLM, we would have a y sub ij, and we would say that that's equal to a beta 0j plus a beta 1j, and then it'd have to be times something. So we would use like an x, and then we would have my r sub ij. Now, in addition to that, HLM has each one of these modeled as a function of something. So at level 2, it's where we have gamma 0, 0, we would have a gamma 1, 0, and then we could have my random effects. Now remember, we could have other fixed effects. We could have level 2 variables that would be like w's in there. Now, no matter whether we put w's in there or not, there's still going to be covariates that each person could feasibly have, thinking how we change things to mixed models. Which means if I were to actually shift this into a mixed model, what we would end up having is that y sub ij is going to be equal to, and here we start to first focus on my fixed effects. So there's going to be a gamma 0, 0 lingering in there, plus there's going to be a gamma 1, 0 times an xij. Now the way I'm getting to this is I'm plugging in and doing the simplification at the same time. But if we took beta 0j and plugged in, so if we actually plugged in beta 0j as this, and the same for beta 1j as this, we would eventually get to this thing that I'm writing out. Now the second piece that we have then is going to be a u sub 0j. We're going to have a u sub 1j times a x sub ij, and then we're going to have an r sub ij. So what's important to notice here is lingering in the background is we've got my fixed effects, which look a lot like regression, and then we've got these random effects, and my random effects are pulling specific random effects for each school. So like if I was using schools. And then we have this R thing sitting here. So when we move to mixed models, the notation starts to change a little bit. And this is going to take more slides. So at the end of the day, this thing's going to take a little bit longer than a quick little 5-minute explanation. First, this stuff looks a lot like regression. And so the notation usually ends up representing something very similar to what we might see in regression. So I'm going to move to the x beta, but know whenever I say x beta, think fixed effects and think gammas. Now, all of this gets added to, and here's where things get a little squirrely, but there's going to be a design matrix that we make very specifically in a very certain way. And then we can use a u. And I'm going to move to another slide, and then I'll talk very specifically about what these things are here in a little bit. And then we have an R sub ij. So right now I'm still using i's and j's. Actually, actually I was still using r's and j's. Let me just switch this up. The other thing we want to do is make this so that these are vectors. They're more like what happens in regression. So that means this y is going to be that n by 1 vector now. It's that whole thing. This x is going to be just like in regression. There's a column of 1s, and then it's like x1, x2, so on and so forth. And my b here are going to be my fixed coefficients. So the notation between the literature for mixed models and for HLM, they don't sync up. My b, in this case, would be filled with the gammas that we would normally see. So those two, notation is different, but conceptually just read b as fixed coefficients. Now I've got my z and my u. Again, I'm going to talk about these things. The actual size of u depends on the number of level 2 clusters. I know you love to hear that. It depends. I'm going to say that level 2 in this case are going to be schools, and we have students. So it's a 2-level model, and based on that, it depends on number of schools and random effects. Z, it's going to have n observations, so n columns, by, and then it really depends on the size. So it also depends on this same thing. And then R is going to be an error vector. So it's a vector full of the errors for every single person. So N in this case is going to be the number of students, total number of students, because now we're doing students nested within schools. So this is total. So notice this total number of students, if I had 10 schools to where each school had 20 students, the total number of students would be 200. And so N in this case would be 200. So R is also going to be an n by 1. Okay, so now we kind of laid out the mixed model. We've got stuff that corresponds to these random effect things, stuff that corresponds to the fixed types of things, and then stuff that's regular regression type of error things. So the first step that we can talk about is, well, what's the expectation of y? So our actual distributions, we're going to start off with y, and we're going to say, well, it's also multivariate normal. And it's going to be centered at x beta. So that doesn't really change. Now, the reason it's only x beta is because we assume all my errors have mean 0. And because all my error terms have mean 0, then the expectation is going to be 0, which means they're adding on 0 to x beta. And as a result, the mean is what it is. It's just the x beta. The next thing, it's this big covariance matrix. Now, for us to know what this big covariance matrix is, we have to understand what these things are, because those are what describe the variability. Remember, if you think back, so this is us thinking back to the previous slide, it was sigma squared times I. It was this big variance covariance matrix to where along the diagonal was sigma squared and the off diagonal were all zeros. So now I'm going to move to the next slide. And the next slide, we're going to focus in on what is z times u and how does r play into it. And then lastly, we'll get to how do we find out my variance covariance matrix. Okay, so going back to my mixed model. Now I'm just going to write it down for a person. I'm going to be a little clumsy with notation. Okay, so for a given person, this is what my mixed model looks like. What's important to notice is these things are school specific. So depending on which school they come from, they're school specific. This is student specific. So how do we get that thing? Like, how do we make it so that for a person it actually plucks out whether or not it's that particular u sub 0j or that u sub 1j? Well, what we do is we take all of the random effects. You can't see my hands because I did not put this on the camera. I should have. We take all of the random effects and we plop them into a matrix. So for u's, let's pretend that I have 10 schools. That means that there will be 10 u sub 0j's, an intercept per school, and there will be 10 u sub 1j's. So in that case, I'm going to have a total of 20 random effects. So there's one per school, or sorry, there's 2 per school. In fact, if I were to write that out, then the u's, the actual u's, I could have a u sub 0,1 and a u sub 1,1. This is for the first school. I can also have a u sub 0,2, a u sub 1,2. This is for the second school. So remember, those error terms, they talk about how a school differs from that grand mean. And so every single school is going to have one of those. In fact, if I continue this on, now I erase these, dot, 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 because dot, dot, dot captures everything. Then in my example, I'm going to have a u sub 0,10 and a u sub 1,10. And so this whole thing is my little u vector. So what we're trying to do now is figure out what z times u is. This thing in my example is going to be a 20 by 1 vector. So what is z? Well, z has to be a way to pluck out those values and also capture the fact that there's this x here. So what happens is then if we have individuals, so at the end of the day, this thing is actually going to be n by, in this case, n by 20, because we have to be able to multiply these, so the 20 and the 20. So this thing's going to be n by 20. Every single student has it. So let's imagine all the students that come from the first school. So these are all students. There's a row per student. But they all come from school 1. And we have to pull out these u's. So what happens is this is a design matrix in the sense that I have a 1 to pull out the u sub 0,1. And then I have an x for that student to take x times this. The rest of these values are all going to be 0. So whenever I do the matrix multiplication, what this ends up equaling is u sub 0,1 plus u sub 1,1 x ij. And then it's a bunch of zeros times things, and so they cancel out. Now, if I look at the second school, it gets tweaked. So the second school is going to have 2 zeros. It's not the first school. But then any individual from the second school is going to have a 1 here, and then they're going to have their independent variable. And understand, this scales. So if we have more independent variables, z gets really wide because it's capturing all independent variables. The more random effects we have, z gets wider. So now I've got this big u vector that's 20 by 20, and now I have this z that is a set of linear combinations of my u's. So that now anyone from the second school ends up with basically 0 times u01 plus 0 times u11. So these things all cancel out. But then they have a 1 times 0,2 plus a 0,12 times x, and then all the rest of this is 0. So we can start to see how this design matrix plucks out the random effects for that particular school. Okay, so hopefully at this point, and again, you may not have it perfectly down, but now we know what z and u is. Now the last thing, and I'm going to squeeze in this little corner, the last thing is r. And r is just like regression. And the reason I say just like regression is this thing is an n by 1 thing. We assume that the elements in it follow a multivariate normal, or sorry, we assume that that vector follows a multivariate normal distribution that's centered at 0. And we make the same assumptions that we do in regression, identically and independently distributed errors. Now, it turns out that we also make identically and independently distributed assumptions about the u's. So for example, anything having to do with an intercept, we assume that these things are IID. So the random error of one school is not related to the random error of another school, but they have the same variance. We also make a similar assumption about slopes. So we assume that they're IID. And we assume that slopes from one school are not related to intercepts of another. So across schools, we assume that error terms are independent. Now, what we do allow for is the fact that these U's can be correlated. Remember now, for us, we had that tau 0, 1. This IID here for intercepts, we call tau 0, 0. And this IID for slopes, we call tau 1, 1 with respect to the variance. Okay, so now we know y is centered at x beta. Now we need to know the variance covariance matrix. So in mixed models, if we go back to it's centered at xb, and then we have a z, u, plus an r. Given x, so given x, the distribution of y, so we say y, really I should be saying y given x, sorry about that, is multivariate normal, it's centered at xb, and now we need to know the variance of this thing. Well, if it's given x, if we compute the variance of this thing, it's the variance of this. The variance of xb plus zu plus r, and now it's given xb. So these are constants at that point. They're known, which means they drop out. So now it's the variance of zu plus r. The variance of zu plus r. Now remember, these are matrices. These are, sorry, z is a matrix, u is a vector of random variables, and r is a vector of random variables. So now we can invoke some of our assumptions. For starters, the variance of zu, this can be rewritten as, sorry, the variance of z times u plus the variance of r. Now the reason we can do that is we assume r is independent of u. Next, the variance of a linear combination of a vector is equal to that linear combination times the variance covariance matrix of that vector times that linear combination transpose. So that means this is z times the variance of u times z transpose. And remember, we now know the structure of z. There may be multiple students from the exact same school, and so they will have similar elements in them. And then we have the variance of r. Variance of r, we're using the exact same assumptions as we did in regression, which means that's sigma squared times I. Again, I is n by n. Z over here is going to be n by that big thing. I'm just going to use 20 here because that was my example. The variance of u is this big 20 by 20 matrix. And then we have z transpose, which is going to be a 20 by n. So we pause for a second. We hold on to this idea. We know what this thing looks like. So we know from regression. So now we know what z looks like. What we don't know, or what we haven't talked about, is what this thing looks like. Now, because I'm using an example, we can talk very specifically about that example. And remember, we assume that air terms corresponding to the same thing, so either the intercept or the slope, are IID. We assume the air terms corresponding to the same intercept or slope are the same. Sorry, here, let's do this. So now I have a u sub 0, 1 and a u sub 1, 1. That's for school 1. We have the same thing for school 2. And I'll just draw my little lines across. Now we're going to have, because it's a variance-covariance matrix, now this is clearly not to scale at this point, but remember there's some dot dot dots, and eventually I'd have a 0, 20, 0, 1, 20. Right, so this thing's a big 20 by 20. For starters, because I'm just going to talk about these two, u sub 0, 1 and u sub 0, 2, they're both talking about the intercept. So they are IID, identically and independently distributed, which means we're going to assume that they have variance tau 0, 0. So this is using that HLM notation. We can do the same thing with the slopes. So they can have a different variance from the intercept, but we assume that all slopes corresponding to the x are going to have the same. Next, we assume that all intercepts are independent of all other school intercepts. So that's what this 0 is. We also assume that all intercepts are independent of other school slopes. So at the end of the day, these things start to all become zeros. Lastly, we actually allow the random effects from the same school to have an association, but we assume that whatever association it is, it's the same across all schools. So it turns out that that little covariance thing here, we assume that they are the same. So at the end of the day, this becomes, if I write out my matrix like this, the correlation matrix of my air terms ends up being this sort of diagonal, or it's a block diagonal matrix, to where we have all random effects within a school allowed to correlate, but we assume that correlation is the same across all schools. And then we assume the same variance and the same variance for the slope and intercept across schools. So that's what U is. Now remember, Z is full of these linear transformations. And so what ends up happening is whenever we take this thing, I'm taking a variance-covariance matrix that is a 20 by 20 matrix, but I have a total of n linear combinations. So there's one per student. And so in those cases, to where two students are from the exact same school, it actually ends up pulling out the exact same components here. And so as a result, it creates elements that are off-diagonal elements. I will give you an example. Let's imagine only 3 students. So I have a student that's from school 1. I have 2 students from school 1. ... 0. Oh, we should have another 0. And I'm going to have another student that's from school 2. So these are the students I'm going to focus on. Now remember, we're multiplying these linear combinations, so this is my Z, and it's times this big matrix to where I have tau 0, 0, tau 1, 0, 1, tau 1, 0, tau 1, 1. And then this is 0, 0, 0. And then I have school 2, which is also going to be a tau 0, 0, a tau 1, 0, tau 0, 1, tau 1, 1. And then this is 0, 0, 0, 0. Okay, so if I multiply z times this, and remember there's a z transpose out here. If I multiply z times this, what happens is this first element pulls out these two things. So that means the first element of z in the first column is going to be a tau 0, 0 plus a tau 1, 0. Now if I move along, that means the second one is going to be a tau 0, 1 plus a tau 1, 1. But then as they stop matching, these are all just going to be zeros. Now this same person is going to look exactly the same. But as soon as we get past people from the same school, these are 0, and now these are going to be tau 0, 0 plus tau 1, 0. And so on and so forth. So when we add in the z prime, and I'm not going to go through the whole multiplication, but when we add in that z prime, what ends up happening, and here is kind of the magic of the whole thing, is when we have a z times the variance of u times z prime, this is n by 20, this is 20 by 20, this is 20 by n. So these can multiply, and I get an n by n matrix. That matrix, remember, so now this each row is by person. What happens is anyone from the same school, they're going to have an association. So they will have variances here, but these values right here along these lines, these will be non-zero. So these will be something not equal to 0. But when we have students from different schools, oh, it's terrible. Then whenever we start looking at the association between a student from school 1 with a student from school 2, these things are 0. So the clustered nature of my students is captured right here. This thing captures those clusters. And then we come along and we add on my variance covariance matrix associated with error. So that means the total error variance is going to be the sum of these things. But then this z times the variance of u z transpose captures a block design in my variance covariance matrix. It's this part right here violates assumption in regular regression. So that means at the end of the day, so now for completeness, if we were in mixed models, my y is going to be an n by 1 vector that follows a distribution that is centered at xb, and it has variance covariance matrix equal to z times the variance covariance matrix of u z prime plus my sigma squared times I. Just for completeness to fill in things, x over here is going to be n by, and now if I'm using p as the number of variables, it'll be p plus 1 because of that column of 1s. B here is going to be p plus 1 by 1, it's a vector. Z is going to be n by, and then it depends, right? It's this it depends. U is it depends by it depends, and Z transpose is going to be it depends by n. So at the end of the day, this thing is n by n. And variance here is 1 by 1. It's a scalar, and I is n by n. And so this thing is also n by n. which means the combined thing here is an n by n variance covariance matrix describing association of, I'm going to put errors, and I'll put it in quotes. Notice these errors, sometimes part of them are random effects. Those are what my U's are. And part of them are then kind of my level 1 errors. Okay, so that is the mixed model and how it models things. It still models the means or the expectation of my vector y in the same way as regression. It's this added part that then, because we're using a 20 by 20 matrix in my example, but I have linear combinations that are similar, so they're actually the same per students from those schools, it plucks out common pieces of my U, which is then what captures the covariation between them. In fact, the off-diagonal elements of this thing, whenever we combine it with this, we start to get at, that's what the interclass correlation comes up to and things like that. So in a simplified example, we could show that as well. So I hope that this ended up helping. Again, if there are still things not clear about this, we can end up talking about it, but this will be at least a start.